Let me thank everybody very much for joining this series, which starts today, lasts for 3 days. Thank very much, Sir Tim, for finding the time, despite the millions of people who want something from him every second, to be there with us. Look forward to welcome Internet father Vint Cerf, who is going to be there today and tomorrow. And thanks for that. And let me introduce quickly Dr. Ben Siegel, who has done his first degree at Imperial College and his PhD at Stanford before he came to CERN in '71 to work on networking. He coordinated in the 80s the introduction of Internet protocols at CERN and taught them internationally from 1986. He participated in CERN's major distributed computing efforts from the 90s, leading to the replacement of mainframes by clusters and then to the grid and cloud computing. Ben is honorary member of CERN and an active advocate of volunteer computing and citizen science. So thank you very much again, Ben, for accepting this invitation for this lecture. I shall now Pascal, can you unmute Ben? Please.
Yes, good.
Ah, fantastic.
Right, okay. I'm going to share my screen. This is a distributed computing historical perspective for which we thank Maria for organizing it. There are going to be 3 talks, and I'm going to start off talking about TCP/IP and the start of Internet at CERN and in Europe. It's not just a historical perspective, but it's also a CERN perspective and to some extent a personal perspective. Next slide, please, Maria. So this story spans half a century, and it's surprisingly little known outside CERN and even within CERN. And it came from a relatively unknown part of CERN, which we'll see later. In fact, CERN didn't actually have the mandate to do this sort of work. But it led to Internet in Europe, to the web and the cloud, as we'll see as the series progresses. So I'll begin at the beginning. The Internet's early timeline. Well, it all started with ARPANET in 1969. ARPANET was not the Internet. ARPANET was a mononet. It was a connection by landlines, initially at 56 kilobits, which was a high speed in 1969, between a small number of university computer centers. And it became the Internet, and we're going to see how. First of all, important developments on the ARPANET included email and certain tradition of Internet standardization, which we'll also see later. So ARPANET transitioned to what we call the Internet by specifications between 1974 and 78, where the original ARPANET protocols were replaced by protocols which would allow the Internet. And these are called TCP/IP. We'll understand why. They were actually introduced on the ARPANET structure in 1983. And a co-specifier is online. Hopefully, there he is. I see his face. Hello, Vint. Vint Cerf is online with us today. And he and Bob Kahn did the specification of TCP/IP with some famous papers. And the actual separation of TCP and IP was done by a third person whose name I forget. No doubt Vint will tell us. But basically, Vint, Bob, and a very few other people. Yes, Vint. Okay. I'm getting an echo. Somebody is not muted. Anyway, welcome, Vint. I'm still getting a terrible echo. Right. Can we find out who is? Are you muted, Maria?
I think so.
No, Maya, you are not muted.
I can only see the slides.
It's okay now. I'm muted.
Yeah, okay, fine. Okay, so could we go back one slide, please? Thanks. So CERN adopted TCP/IP protocols within CERN as a test for 5 years, starting 1984, and I coordinated that, as we'll see later. Very, very few people participated in that, and CERN joined the real internet in January '89. Next slide, please. So ARPANET then showed the way to an internet. We thank Vint Cerf and comrades for their work to do this. By the way, I met Vint for the first time in summer 1978, where he was presenting a paper at this Advanced Study Institute on the interlinking of computer networks, of which you can find the full articles online, by the way. It was the only time I've taken military money in my life, because this institute was funded by NATO. Okay, next slide, please. So what were the basic principles of TCP/IP? It came from deep thought and experiment. The main principles were this. First of all, use packet switching, not circuit switching as for telephony. Use a global numbering system so that processes, hosts, and networks had unique global names. Use layered protocols, but not excessively so. The next slide will go into that. Provide IP datagrams on all networks and media. This is the key to everything. Use best effort IP delivery and smart routing algorithms, routing, as we say in the US. And provide fragmentation and reassembly for IP at the IP level, because packets cannot be guaranteed on every media to be transmitted at a given size. Some media restrict packet size differently from others, and so you have to be able to fragment and reassemble IP. All this being done below the highest level, which is Transmission Control Protocol, TCP, where reliability issues and error correction is done end to end. And finally, provide a standard programming API known as sockets from Berkeley. So those are the basic principles of TCP/IP. They're simple and they work. So the message is internetworking needs IP. Next slide, please. About layers. We'll be talking about protocol war battles a little bit, and one of the battles was about layers. The main competing system for TCP/IP was the International Standard Organization's proposed open systems integration. It had the famous 7 layers, 7 main layers. It also had numerous sub-layers. The OSI layers only communicated with their immediate neighbors, imposing multiple copying of data between layers. It was a good idea to separate the layers in principle, because if you changed a layer below, you didn't have to change all the layers above. But the copying was a very big handicap. TCP/IP has only 3 layers below the application layer, and it avoids copying between them. 3 layers are the link layer, where the actual media is handled. So you encapsulate basic data on the media. Then the crucial layer is the IP middle network layer, where this uniform datagram layer is done, which assures best effort delivery from the host system to the destination system. And finally, the TCP transport layer, where the error correction reliability is done. a famous saying by Michael Padlipsky, a polemical gentleman who wrote a book in 1985 that some of us will remember, called The Elements of Networking Style. And he said, if you know what you're doing, 3 layers is enough. If you don't, even 17 layers won't help. Next slide, please. The protocol war was also about standards and how we set them. The ISO style of standards development was top-down, driven by committees of experts meeting physically from time to time, usually in nice places like Copenhagen and so on. The ISO standards were printed for sale and were expensive. Internet standards, by contrast, were developed bottom-up and free online. Internet standards documents were just called request for comment, very modestly, and these standards were iterated using test implementations. This was a disruptive victory of bottom-up over top-down. The famous saying by Dave Clark in 1992 at an IETF meeting, and IETF was the lowest level Internet Engineering Task Force, standard setting meetings where debates took place among anybody, and those people considered worthy of having their comments listened to and adopted usually prevail. And Dave said, we reject kings, presidents, and voting. We believe in rough consensus and running code. This is really the motive, the essential motive of the internet development. Okay. So let's look back to the 1980s. We're going to look at CERN. We wanted to solve a technical problem, sharing data between different sorts of computers. We had a huge amount of different sorts of computers. We had many different manufacturers. Each manufacturer had their own operating system. They had their own machine code. They had their own hardware representation. They had everything different. And sharing data between them seemed to be impossible. So in 1983, my boss, Les Robertson at the time, head of the software group, asked me to look around for some solutions. We found TCP/IP. It was easy to find software. We began to install test versions. Soon we connected mainframes, the big IBM VM mainframe, the Cray, which already had TCP/IP on it, actually a very nice implementation. Digital's biggest machine, the VAX 9000. Medium-sized computers, the VAX VMS machines, Unix, workstations, and IBM PCs. We could find software. Sometimes we had to pay for it, but very often it was free. And it worked well. But we were not supposed to go beyond testing. We'll see why in a moment. In principle, we were forbidden to connect machines outside CERN. We'd hit a massive wall, but a non-technical wall. Next slide, please. Networking in the 1980s again. Political, economic, and social issues were present. Computer firms were competing. As we'd seen, their products were incompatible. They were not cooperating. The national telecom monopolies had dominant power. You couldn't just choose who became your network provider. If you were in Switzerland, you had to go to the Swiss PTT, Post Telephone Telegraph Monopoly, and do what they told you. The networking technologies that were being sold by the telecom monopolies were slow, expensive, and often incompatible. The paradigm, because they were basically telephone companies, was circuit switching and charging by data volume. But TCP/IP wants best effort datagrams and lightweight accounting to succeed. Next, please. More problems with our technical solution. TCP/IP was US developed. It was not an international standard, so-called. The international ISO and ITU, International Telecommunications Union, didn't even talk to the internet standards bodies in the 80s, the IETF and the IAB. TCP/IP was explicitly opposed by the European PTT monopolies, particularly the German PTT monopoly, which was feared by everybody, including the Swiss. By contrast, TCP/IP was cheap and simple. In fact, it was disruptive. There were these alternative solutions being offered. There were proprietary solutions by the manufacturers, the computer manufacturers. They had powerful supporters. For instance, Digital Equipment, which has now disappeared as a company, had a system that the CERN physicists loved, PMS, and they had a beautiful network called DECnet, which was very well integrated with the operating system, but was incompatible with other things. And Digital did not provide a TCP/IP option on their VMS system. They did provide it on their Unix system. In fact, a protocol war was being fought over them. And crucially, CERN did not want to fight battles over networking. Next. Let's look at the power structure inside CERN, the political order. It's still very similar today. There are some differences, but basically, this is what CERN looked like. King at the top are the physicists, and second, just behind, are the accelerator engineers. Then there's the rest. Inside the rest is computing. The order in computing had a hierarchy. Big mainframes, IBM, Cray, etc. Big peripherals, expensive tape robots, the big storage systems, the big disks, the tapes, except the tapes, and the rest. Inside the rest is networking. But there was an order in networking. The external lease lines running either the IBM or Digital proprietary protocols, or X.25, which wasn't a complete protocol set anyway. The internal networking, which was the CERN home invented network called CERNet, and the big effort to cable up the laboratory with Ethernet. And down at the bottom was internet and distributed computing. So right at the bottom of the bottom, this is where we had to work. Next slide. Okay, some good news. In early 1985, I was named CERN TCP/IP coordinator. Remember, no external connections. It was just installing and coordinating the effort inside the lab. I had no resources, but I was supported by the software group, which I happened to belong to. CERN's main computer networking group did not cooperate. I held weekly coordination meetings. I bought licenses when necessary, distributed them. I managed all CERN's IP numbering. I could do it completely independently. I chose network 100, which will amuse some of the people present. We used static routing tables. There was no routing. The LEP experiments interconnected their CERN machines, not to their experiments, but to each other. And the powerful LEP SPS controls group adopted TCP/IP for LEP. LEP was the big accelerator in the same ring we have for LHC, the 27-kilometer ring, and that was the project at the time. So the fact that they chose TCP/IP was a big plus for us. They had no other choice because they had decided to adopt an IBM token ring to go around the ring because they were frightened that Ethernet wouldn't make it. I think Ethernet repeaters weren't even invented at that time when they started. And so in these years, many initial testers became enthusiasts and actually became dependent on the system. We were taking the first steps towards our dream of distributed computing. Next slide, please. What was life like in the underground? This is these 5 years between 84 and 88. The ups and downs of working bottom up, the downs. It's unpleasant to be treated as an outlaw or a threat, particularly when it went on for 5 years. It's demeaning when the division leader writes in 1987, TCP/IP network is not a supported service. He'd had some complaint from a user somewhere about some aspect of TCP/IP. But it had ups. Working informally like we had to was perfectly in the internet spirit. And I was allowed to teach TCP/IP and network programming inside CERN and outside internationally. I had one particular student, which we'll talk about in a moment, but we were still forbidden to connect machines outside CERN. Then, very good news. In late 1988, CERN finally accepted that ISO-OSI was not coming and allowed CERN connections outside. The CERN networking group finally stepped up and took over TCP/IP support. IBM helped by paying for CERN's USA link. Turns out that IBM had switched policy a few years before this and started to encourage people to use TCP/IP. They had a program called EasyNet with big European customers like in CERN, Italy, France, etc. And they linked these together by paying for the links. CERN very rapidly became a main European internet center. It went very, very quickly. Within 1 year, I think CERN was the biggest center in Europe. And this allowed us to adopt internet standards for email, file database sharing, remote login, remote procedure call, etc. In other words, we were on the way for distributed computing. Maria will talk about email next talk, and we'll see how it goes. Next slide, please. The particular student I mentioned was Tim Berners-Lee, who is online. Hello, Tim. He came to CERN as a fellow in 1984, after a short stay in 1980 as a contractor. We met around 1985. He came to ask for advice on his official project, which was to develop a remote procedure call project. We'd done a little research in RPC, and it seemed promising to us, but we'd never done anything serious with it. And then this young man comes and makes a fantastic job of RPC. He programmed it and set it up on all sorts of systems all over CERN. Quite amazing project. I taught him TCP/IP and network programming early on. I think he probably learned it in about 30 minutes. He did ask me for some ideas when he was designing HTTP, and I showed him the RFCs for NNTP network use protocol, use transfer protocol, and the file transfer protocol, which a few of the features he put into HTTP. I helped him get a next machine by talking to his boss, who was a friend of mine, who, with a twinkle in his eye, agreed that Tim could prototype his funny idea on it. I wrote a reference for Tim's indefinite contract, maybe he doesn't know that, and which he got. And I helped him get 2 student collaborators, Nicola Pello and Jean-François Groff. Of course, his invention changed the world. Maria will speak more about this in talk number 2. It's a great honor to see Tim here, and I hope you'll have time to have some words when I finish. Next slide, please. This was the famous reaction of his boss to his first proposal, vague but exciting. It got filed away and more is forgotten for another year or 2. Tim is online with us today. Next slide, please. Distributed computing progressed. By 1989, we realized that the mainframe model for physics production computing was not scalable. Network nodes of powerful workstations could do better. In fact, at one point, we set up one powerful workstation, an Apollo DN10000 with 4 processors in the computer center, hooked it up to the data, and very soon we were generating 25% of the entire computer center output with this one machine. So the director called up, he called me and he called Les and said, "What is this machine?" It was called Hope. What is this Hope? And they explained that it was this one machine, and it was hooked up to the Cray, because the Cray was the only machine that could stage tapes. We could only hook up Ethernet to the Cray, and then we told the Cray to stage tapes, and we could get data from the tapes and crunch it. So then I got a call from the director saying, "How much resource are you using from the Cray?" So I calculated it was about 0.5% or something. And I never heard from him again, but they weren't too happy about this at the time. However, the division head did support us with this project called Shift, on condition that we could get support from one of the big 4 experiments of LEP. And the Opal experiment gave us support. The system, we made it look like a distributed Cray supercomputer. The architecture for it will be described in the 3rd talk that Les and Frederick Hemmer are going to talk about. And we started in 1990, and by 1992 it had clearly succeeded and was very widely adopted. And that led directly to grid and cloud computing. Next slide, please. We actually won a prize for that 10 years later. We were proposed for the prize and by, I always forget his name, the head of Oracle. Anyway. So there in the picture you see, going from the right, Frederick Hemmer, Les Robertson, Jean-Philippe Beau, Bernd Panzer. This is Gail Hansen, a physicist from Opal. This is Matthias Stroeder and myself in the computer center 10 years after shift began. So we'll hear about that from Les and Frederick. Next slide. I think it's about the final slide, about innovation. It's surprising how 1 or 2 gifted people are often the most effective for real innovation. As we see on the left, TCP/IP, 2 main people, one of whom is here. Unix, 2 people, Richie and the brain is going. Richie and, anyway, there were 2 at AT&T. Google, 2 people. HP, Hewlett-Packard, Intel, 2 people. And then the web, 1 person. Linux, 1 person. Amazon Web Services, actually 1 person, a guy called Chris Pinkham had that idea and managed that program for quite a long time. And Ethernet, 1 person. True innovation is unpredictable. It involves chance and coincidence and remains a mystery. History does not crawl, it jumps. Last slide, please. All right, the next 2 talks, Maria tomorrow, and Les and Frederick the day after. So just the final thing, we didn't know that the world was going to change when we were doing this work. We've just made pragmatic choices as far as we could. Keep it simple. Luck and serendipity helped a lot. So for the younger people present, if you want to innovate, make good, simple choices and be in the right place at the right time. That's the end.
Thank you. I need somebody to unmute. Am I unmuted?
I will mute.
I will try to.
Yes.
I'm unmuted now. Thank you so much for the talk, for these nice details, history. Let me, in 1 second, as a sponsor, allow me to welcome Vint Cerf, who together with Tim made the time for us today. Thank you very much. I think that before we start raising hands, we are quite numerous now. Just wanted to clarify that tomorrow, Nathaniel will also share part of the talk, and he will speak about his invention, which is the multi-purpose internet mail extensions. And before we start watching who raises hands, if Tim, you have to go very soon. If you wanted to make a comment for the talk by Ben now, before you go, if you have any.
Sure. Yes, thanks, Ben, for that talk. It was I knew most of it, but one piece I thought that in history that the internet had been tunneled over the IBM, had been surreptitiously tunneled over the IBM protocols that IBM understanding initially, but that was maybe too fancy. The IBM actually did approve of it and officially switched to TCP/IP to the internet. So that's good. So thanks. I say also thanks for the talk. Thanks also for the help for the pointing me at the socket interface and yeah, and at the RFCs. So looking at basically the way FTP protocol works and the way the NNTP protocol works, you can see that basically the HTTP protocol was basically something just taking pieces out of that. It was all just like FTP, but a bit simpler, a bit like an NTP, but a different sort of workflow. And so so very much there was a feeling that the people who are developing the world, the internet and the world around it were close. You know, they're doing things which are very related. They got very similar motivations, and all I had to do was to take a little bit of those protocols, and then look at what the people are doing with hypercard protocols. Similarly, people do hypertext systems. They were well sort of understood. They were simple things where you click, go somewhere else, and so similarly. And CERN used say this HTML syntax for its pages. So all I had to do was sort of as a matter of policy was to just use the existing standards that people already used out there, and then that people would look at it as a sort of agree and just take it away and use it. So those were great times. It was great to be part of in a way of that internet community, although most of the community were in the US, but certainly we had, thanks largely to you and your channeling or everything which was internet technology, internet culture as well. We had a sort of little oasis of internet in CERN as well.
Thank you, Tim. It's amazing how modest you are. You say CERN, you chose HTTP, like it's instead of saying that you initiated this, the hypertext-based project tomorrow in the second talk. It is also amazing how many times the proposals had to be put on the table, 3 times. Anyway, congratulations for your inventions and your modesty. Does Vint have something to say now before people start raising hands? Because we are 141. I will have to manage this.
You clearly have put together a very popular program, Maria, and it's lovely to see you and Tim and Ben, and to listen to Ben's story, which I knew a lot of, but never told quite in that beautiful linear way, with all of the battles that you fought inside of CERN. In a way, it's completely ironic that Ben and Tim both had to fight at CERN in order to get their ideas accepted, and yet we can now look back and say that CERN was a place where some very important events occurred, not counting, discovering the Higgs boson not too long ago as well. But the fact that people had to fight in order to get their ideas pursued, I think is an important observation. Persistence and patience count in many of these circumstances. And I can tell you that in the case of TCP/IP, although Bob Kahn and I started working on it in 1973, based on a lot of our experience with the ARPANET, it still took us 10 years to get to the point where we could turn it on. And of course, as Ben well knows, about 1978, just as we're freezing the TCP/IP spec and getting implementations done on various operating systems, the ISO team started working on open systems interconnection with their first architecture document that came out in '78. And that tussle continued until 1993, certainly here in the United States anyway. So again, another big 15-year odyssey. So I'm so glad that you're putting these things together, Maria, because history is easily forgotten, and it's much more fun when it's told by the people who actually lived through it. Exactly. So Ben, let me thank you again for a really lovely presentation. I will take issue with, excuse me, one thing. In the case of Ethernet, there really were 2 people, Metcalfe and David Boggs, who sadly passed away recently. David was the engineer who actually built the piece of equipment. Bob came back with the idea from Hawaii, thanks to the Aloha Net. And ironically, just another little piece, Maria, is that Metcalfe wouldn't have known anything about the Aloha Net if it weren't for the fact that he'd stayed in Steve Crocker's house And those of you who know Steve know that he was a key party in the ARPANET development because he led the group that did the host-to-host protocols. So Crocker had an article about AlohaNet in his dining room table that Metcalf saw, and it triggered his interest to go to Hawaii for a month. And he came back with the idea of making the AlohaNet run on an optical, or I mean on a coaxial cable at 3 megabits a second. So the history of technology is never exactly straight.
Hey, can I ask one question?
Yeah.
Who was the third guy at Stanford who did the separation of TCP and IP?
Oh, actually, there were several people that were promoting that. First of all, there was a guy. It wasn't actually at Stanford. It was at USC, Information Sciences Institute. Danny Cohen, John Postel, and David Reed at MIT were all big proponents of datagram and communication that did not require sequencing.
Right.
They were more interested in low latency, which, by the way, you will have noticed has suddenly become a big deal in 2022. Everybody's interested in low latency applications. So they were looking at packet speech and packet video.
Yes.
And radar and things like that, where it didn't matter if you missed something because something was coming immediately thereafter. The next thing was going to arrive. So retransmission wasn't necessary. And so that's, there wasn't anybody specifically at Stanford that was pushing that. At the point where we did that split, it was 1977. By that time, I was at ARPA.
Right. No, I saw at Stanford, there's a plaque. There's a plaque of internet heroes. And on the plaque is the name of this guy. I think it's an Indian guy. I don't have the name in front of me. And he gets credited. And also on Wikipedia.
You're thinking of Yogan Dalal.
That's it.
And yeah, Yogan is one of my graduate students. He and I and Carl Sunshine wrote RFC 675, which is the first detailed spec in 1974. But actually, what you should be remembering is not the split of TCP/IP. Yogan is the one that figured out with Ray Tomlinson, who's the inventor of network email, that they needed a three-way handshake in order to deal with sequencing of the two pieces of the TCP protocol, either side. So he did the three-way handshake with Ray Tomlinson.
Thanks a lot.
Amazing. Amazing how history unfolds in front of us. I don't know what to say. It is just, and how you remember your student of 1974. It's amazing. I don't know. It's great people you are, all of you here today.
Yeah, Maria, it's Vint again. Just to observe, the ARPANET project got started around 1967. And so we're talking more than 50 years ago, these ideas were becoming fruitful. And the X25 work, which worked very well, is a popular international standard, comes out around 1976. So there's quite a long story here, and it isn't over yet because we've got 5G and 6G and Wi-Fi 7, and there's just a bunch of things happening.
Exactly. Tomorrow, there will be some of this material that you are mentioning, and I'm so grateful that you can also join. That will be also repeated or analyzed from a slightly different perspective. Thank you so much. So now the question is concerning Tim, if there is something else, if he has to rush, if people would like to raise hands. I don't know otherwise how to manage video. I see Harvey Newman is here. Amazing. Harvey, go ahead, please.
Oh, thank you very much. This was really fantastic, Ben. I wanted to mention just very briefly from a different point of view, CERN is also a place that brings together technologists and scientists from all over the world. And a critical thing that happened at CERN was the rise of scientific collaboration, which reached a critical point where the scientific collaboration could not function without long-range networking. So I arrived on the scene around that time, around 1981, and was faced with this issue. And I mean, it was really a marvelous time. I mean, as scientists, Vint just mentioned X25. You know, as scientists, we look at all these protocol possibilities between X25, DECnet, TCP/IP, sometimes one layer on top of the other, or the second layer on top of the other, and went through all of this. And I think it was the CERN environment ultimately was a great place to deploy some of this. Let me just not go on too long, but let me just also remember that there was a critical aspect. You mentioned the IBM support for the link across the Atlantic, the T1 link. In fact, I was involved with that with Al Weiss, where it came to see us and said they were going to support a link from Daisy to the US, Daisy in Hamburg. And after a day of meeting at CERN and seeing the scientific program and seeing our issues and our developments, they changed on that day, they changed from Daisy to CERN, and then supported that link at a very high cost for 3 years. So thanks very much for this opportunity and this great presentation, Ben.
Thank you. Thank you very much. Anybody else who would like to make a comment or ask a question in this unique opportunity?
Maria, there's a question in the chat from Fabian Vanley, who says, if you could go back in time, what would you change? And so, Ben, that might be aimed at you first. So why don't we find out if you have an answer?
Yes. I don't know. It would have been nicer if there had been less nastiness involved in the opposition. But I think a certain amount of nastiness helped. Certainly, Maria, you need to unmute. I've said in other talks that a lack of resources certainly helps. If you have a few smart people, you're in a better shape than if you have 100 or 1,000 people, like on IBM OS 360. You know, they had 1 million monkeys, and it still wasn't very good. But so a certain amount of informed opposition helps. But what we were up against there was it was what I call the sheep effect. When a whole bunch of sheep is going one way and you want to go another way, life is tough. So I would have liked to have changed some of the personal aspects of that, but otherwise, I think we were lucky. We were lucky we made the good choices at the good time. And I think you'll see this continue in the next 2 talks you're going to hear. It's also a question of choices. Tim's work, for instance, is a fantastic demonstration of how you pick out the right cherries, exactly right, and put them together. It's an absolutely prodigious story. And also with Shift, the fact that you could show easily that the mainframes could be replaced economically and elegantly, as long as you based it on things which had been taboo. Unix was taboo at CERN up until the mid-1980s. You needed Unix. TCP/IP was accelerated by Unix in the Berkeley system, and so on. So you need these coincidences, and you need a certain amount of opposition to sharpen your weapons.
Thank you. Very distilled wisdom indeed, after having observed it throughout the years with those people. And Tim, I remember he said when eventually he got the green light about this hypertext project, why don't you go ahead and do it, that Mike Sandel said, etc. I remember him in the cafeteria saying, we are now allowed to ask people to join, especially if they can write code. It was very nice because he did it all by himself. So yeah, you are right. I think the only, Denise, yes, thank you. Please go ahead.
Yes, in reaction to the what would you change? In fact, I loved Ben's talk very much because it's very simplified and the key points really did come out. Of course, at the time, everything's much more complex, and in particular, the lack of address space was the big issue at the time. And it's so interesting now that even now IPv6 is really not so advanced. But I think we saw that there would be a problem with TCP/IP address space. So moving to that, we knew there would need to be a new version of that or something else. And that was a key part of why there was a discussion over which protocol to use. So I think that's quite an interesting one to add into it, especially as people went to so much effort to not move to a bigger address space, and we had gateways and all various solutions there to avoid hitting this big address space problem. And it's incredible that we're still running today on IPv4 address space in most places.
Thank you, Denise. In fact, Vint has commented in the chat. Maybe you would like to mention or
Well, two things. Denise is right. Yeah, we're still pushing hard to try to get IPv6 implemented. It's in most of the routers and most of the edge devices all have v6 capability, but a lot of the ISPs haven't turned it on yet. It's about 30% penetrated, on average, and it's being tracked very carefully by the regional internet registries, especially Jeff Houston at the AP-NIC, who's their chief scientist. I was going to tell you, though, that at Google, we have a very large internal network that links our data centers together, and we ran out of IPv4 address space in that network, and we had to switch over to IPv6 internally just to deal with the expanded space. So that was sort of an unexpected irony.
I am not sure if Harvey's hand is forgotten from the previous comment, or if he wants.
It's a new comment.
Sorry, and then it's Les, but
yes.
Then Les will speak without raising hands. Very good, Harvey, go ahead.
So yeah, regarding IPv6, I mean, just like in the early days, very recently, trying to meet the challenges for the LHC and high luminosity LHC program, we were driven to get our own IPv6 address space at Caltech, and we also have perhaps the first science project that will use the IPv6 address space very extensively, with multiple virtual addresses on physical interfaces in large numbers, and an overlay at layer 2 and flow management at layer 3. And none of it would be possible without these new features of IPv6, but also a lot of the recent developments, I mean, which are also very interesting. Like, again, like in these days, there's such a dynamic situation happening with segment routing, with various ways of making stateful decisions across complex networks. And it's just happening, just like in those days.
Thank you.
I suppose when looking about things, how would you have done things differently? If you can imagine that the world had asked me to design the web and I could start from scratch, then I wouldn't have used HTML. I wouldn't have used, the HTTP and HTML are completely different languages, but but the important thing with the design was the people who were already in the field had to recognize it and think, yeah, I can work and feel I can work with it. So hence HTML had to look like HTML, and HTTP had to look like FTP and so on. And URLs, the had to look like, well, there was only one place where I'd seen people taking a file system on a computer and extending it to now have the computer name on it as well. And that was the Apollo domain file system. I didn't have an Apollo, but the people that I came across this and looked at this, the people who had Apollo machines could just directly address files on other and browse files on other computers in the lab within the LAN. And so they used a double slash. If you want, you start with a slash, it means it's on this computer. Double slash means on another computer, and then there's the computer name. And so I thought, okay, I'll use the double slash, and that then anybody who's come across the main system will be able to use that. And then after that, sort of the having a colon is pretty obvious. You know, lots of things start with the colon, and so having the URL scheme start with a colon is pretty obvious. So hence HTTP colon // Now, in fact, the way it works is if you've got a link from one website to another website, but they are both HTTP, you don't have to put HTTP. You can just start // because all the rest, as long as the scheme is the same, you can start with // and that's why the // is useful. But nobody does that. If they either have they either start with HTTP or they start with a slash. They never start with // And so, in fact, that means we could redesign it. I could have designed it to not had that // and that's so we could have just been HTTP colon CERN.ch / and so on, and that would have saved so much typing, and it would mean people wouldn't have to replace the / key on their computer, their keyboard so often and stuff. But there you go. Once you got to pick what other people will appreciate, will feel like in code to, will recognize. You got to pick the languages, the technical languages of the day, and talking them so that people, so you can bring people on board. So we're left with the //
Thank you. I remember so many times you mentioning in the early 90s that you could have avoided the HTTP colon // etc. In fact, you are right. One has to be based on what will fly and what is known there. And Harvey has put a comment there about the creation of the Apollo room at CERN in 84, 85, and next to his office in building 32, the Rubia building, I think. And the Apollo distributed file system was greatly appreciated. Anyway, so while Ben and Harvey chat, I would invite Les to make a comment. He said he wanted to.
Okay, thanks. You hear me? Do you?
Yes, very well.
Okay, I have a couple of comments. One is a very much a CERN one, which is, this is nothing really to do with TCP/IP or these things, but I think it's worth mentioning that we had this CERN Internet Exchange Point, which was set up by Olivier Martin. Now, the CERN computing room is exactly on the border between France and Switzerland. And Olivier cunningly invited the French carriers and the Swiss carriers both to come and install their equipment at CERN. And so we ended up with this Internet Exchange Point, which was actually part of the Swiss system and part of the French system. And the result of that was that as people started to improve the bandwidth available, put in their additional fibers and all the rest of it, the obvious place to do it was to come to CERN. And I think that was a very important thing later when we started, especially in the grid, and we were able to get very good network bandwidth. The other thing I wanted to say is, I mean, Ben's been talking a lot about how you have to push against the establishment often to get things done. I would just like to say that I always found pushing against the establishment to be highly stimulating. And I think it really helped a lot. And I've been on both sides. I've been pushing against the establishment and I've been the establishment. And I can say that in both cases, it's very good. I mean, on the last project I was on, the grid, I was probably considered by many to be in the establishment. And I found that people like Harvey and Federico Carminati and some other people who are extremely, extremely stimulating in the way that they come along and tell you how you're doing it wrong. And so I think that this is really a good environment to be in. And I think it's something which CERN, you know, which was always, you were always able to do this at CERN. And I think that was a great part of being there. Okay, that's me.
Thank you.
A great environment to be in.
Oh yeah. Can I speak? Maria?
You can, but Tim was saying something.
Sorry. Tim, go ahead.
I was just going to say, it was, no, those were the days. So building 31, where my office was next to the computer center. And later I was, and so it was great to have people like Ben and the computing network division in the same room. There was also, of course, right across from was Tortella's, or okay, restaurant number 2. So just to be able to wander across and or have a coffee, and with that the incredible richness of the people who came to work at CERN, just, you know, coming from all different languages, all different computer languages as well, be able to go and have a coffee or lunch, look at, and then sit in the balcony of restaurant number 2, looking out over the vineyards, watching watching the sun on the Alps on a good day. That sort of the whole environment I found at CERN was really amazing, and a tremendous privilege to be part of it. And I was actually, so I started off moving 31 and then moved across into the building, which was actually part of the computer center. Although, so there were people doing operations in the same room. And I remember one Christmas, I wanted the system to keep running over Christmas, because CERN would, we all had to leave Christmas. So I wanted my next box, my next cube, to keep running on the internet. And there were, on the wall, there were black plugs and orange plugs. And I thought, okay, if I plug in the orange, because my office is now next to the computer center, I get these orange plugs. And so I could plug it into the orange plugs and let it go down. So I plugged it into the orange plugs, and I discovered later when I came back the next year, after the Christmas break, that actually wrong choice. The orange ones are the special ones for the computer center. Maybe I got this wrong. And the whole computer center is closed down over Christmas to save huge amounts of energy. And so all the orange plugs go. You should have plugged it into an ordinary back one. So, well, that's maybe the color codes are different now. But anyway, so it was, but it was great to have been able to plug my little original X computer in, hopefully, you know, near such a massive computer center with its spinning flywheel. Do they still have that? Do you still have that? To just in case power generation. Cool stuff.
Wonderful. Selective memory is a wonderful thing, because you present things as if they were so great, whereas we don't all live it like this. Anyway, so Ben wanted to say something, and then Denise.
Right. So first of all, I can see even Tim can make bad choices. That's a surprise to me. Now, for Les, I can't resist this. Les is one of the most modest people I know, and I have to say this again, I've said it before. Most of this stuff, except the web, would not have happened without Les, or wouldn't have happened here or so soon. We had to drag Les to Los Angeles to get that prize for Shift. We had to physically put him on the plane. He said, "Oh, I don't have an evening jacket," or something. So Les is too modest, and Les led the TCP/IP, supported it. And when he explained how he dealt with political opposition with a smile and even enjoyment, this is so true, and it's so necessary. It's something that I personally cannot do. And without Les, none of this would have happened, from my point of view.
Thank you. I share this exact opinion. Denise, please.
Yes, I just wanted to add a little anecdote. As Tim mentioned that his office was at one point in building 513, where we have our computer center. I don't think many people may know, but inside the TCP/IP network, there's a number called the ASN, the asynchronous system number, is it? Vince can...
autonomous, it's Denise, it's
autonomous system. Autonomous system number. So this was numbered 513 by my colleague Jean-Michel Joannego, who was setting up the internet infrastructure in CERN at the time. And that was numbered 513 because our computer center was in 513. And it's just a little anecdote, and it's where Tim had an office at one point. So 513 runs through a number of things in the history of TCP/IP at CERN.
Very good, exactly. Thank you so much. Is there somebody else? I don't see some hands. Otherwise, tomorrow there will be a lot of overlap. I don't know if Bibo is still around, if he wants to share something from the... Bibo is there, but he's very modest as well. The conclusion I have from...
Actually, I don't have anything to add, Maria. I'll try to think of something to say.
No worries. Tomorrow you have another opportunity. There is no problem at all. We have 3 days of this series. Thank you for joining. It's very kind of you. So having said that, now let us wrap up for today. Thank you all for staying so numerous until the end. I would like to thank so much Tim and Vint for their time and for their wisdom. And the conclusion is one has to be able to be focused, therefore have good ideas, new ideas, and do actually the hands-on by himself, and not take anything personally. I refer to Les's comments and Tim's comments and Vince. They don't want to promote their own persona via this good work. They just want the good work to be done, and they do it, and that's wonderful. So thanks very much, everybody, and hope to see you all tomorrow, those of you who can. And thanks, Tim, for today. It's just wonderful. Thank you.
Thank you, Maria. Thanks.
So it's good to see you all, and I will be here. I'll be here tomorrow as well, Maria. So
thank you so much. It is so great. Thank you.
Bye-bye. Adama.
Bye.